Hello, and welcome to Science for Sleep. I'm really glad you're here. Maybe you're listening in the dark, tucked into bed, or resting somewhere quiet, letting the weight of the day fall away. Maybe you've been thinking too much, or maybe not thinking at all, just hoping for a little peace. Wherever you are, this space is for you, a place where science moves gently and questions don't need quick answers. You can breathe here. You can pause. This isn't a lesson. It's not a lecture. It's something slower, softer, like sitting beside someone and wondering aloud. Not to solve, just to notice. The world moves fast enough already. You don't need to, not here. Tonight's story begins with something simple. So simple, in fact, that most of the time we barely notice it. Time. Not what time it is, but what time is. Not the numbers on a screen, not the voice from your phone saying it's 9:42 p.m., but the thing underneath, the thing those numbers are trying to describe what even is time. We use it constantly, we chase it, we measure it. We say we have too little or too much of it, but we almost never stop to ask what it really is or where it comes from or whether it's the same for everyone everywhere. That's the question we'll follow tonight, quietly, patiently, without rushing to find an answer. Does the universe know what time it is? It sounds like the kind of question you might ask half asleep, like something a child might whisper when the room is dark and everything feels a little bigger. But the more you think about it, the more serious it becomes, the more puzzling. 'Cause we live in time. Every breath happens inside it, every memory sits behind us in it, every plan leans forward into it. But does the universe keep track of any of that? Does it know when now is? Or is time something we've invented? A way to keep ourselves from getting lost? What time is it where you are? Not on the clock, in your mind. Does it feel late? Does it feel early? Are you in the middle of something or slowly winding down? Sometimes time stretches. Sometimes it disappears. A single minute can feel like an hour, or an entire afternoon can vanish before you know it. We think of time as constant, but our experience tells us otherwise. And it turns out physics agrees. Time isn't fixed. It isn't steady. It bends, it slows, it behaves differently depending on where you are, how fast you're moving, and what's around you. That means your time right now might not be the same as someone else's, even if you're side by side. So what does that say about the universe? About how it holds everything together? About whether it even needs time to do what it does? That's where we're going. Gently, carefully. We'll talk about relativity and clocks, and why time might not be what we think it is. We'll explore what happens near black holes, what time looked like in the early universe, why your future and your past might be more connected than they seem. But we'll do it slowly, one idea at a time, one quiet question after another. And if this kind of slow science is something you enjoy, if it helps you think more calmly or even fall asleep, feel free to subscribe or leave a like. It helps this space grow, and it helps others find their way to it too. Now get comfortable. Let your eyes go soft. Let the day fade back a little. There's nothing to keep up with here. Just listen. Just breathe. You don't have to look far to notice that time doesn't always behave the way we expect. Sometimes it feels like it moves quickly, sometimes slowly. You've had days that vanished before you could catch up with them, and nights that stretched endlessly even though the clock barely moved. That difference between the time we measure and the time we feel is easy to ignore, but it's there quietly shaping everything. And once you start noticing it, it becomes hard not to ask, is time as steady as we believe? Or are we just used to pretending that it is? This is where the question starts to grow. Not just what is time, but is time the same for everyone? And deeper still, does it exist in the same way for the entire universe? That's where we are now. Not trying to answer that all at once, just sitting with the question, letting it get a little heavier. Noticing the strange way it pushes back when you think about it for too long. Start with something familiar. A clock. Any clock, the kind on your phone, the one built into your microwave, a wristwatch, a digital timer counting down in a lab somewhere. They all tell time the same way by breaking it into equal pieces. Seconds, minutes, hours. But what are they actually measuring? Mechanical clocks measure movement, gears turning, pendulum swinging, hands sweeping. Digital clocks rely on electrical pulses or vibrations in crystals. Atomic clocks, the most precise we have, use the vibrations of atoms, incredibly fast and incredibly consistent. But even those aren't measuring time itself. They're measuring change. Regular, repeatable change. In physics, that's what time really comes down to. The progression of change, one state becoming another, a system evolving, a signal shifting. It's not a thing you can point to. It's not a substance. It's a relationship between now and later, between before and after. That's where it starts to feel a little unstable. 'Cause once you define time by change, then in places where nothing is changing, what does time mean? If you were floating alone in space, far from stars, far from any motion or sound or light, completely still, how would you know whether a second had passed, a minute, an hour? Without movement or memory, what's left of time? That's not a trick question. It's an actual problem. In physics, the answer isn't obvious. Some would say time is still passing. Others would argue time doesn't really apply without events to mark it. It becomes something theoretical, present in the equations, but absent in experience. And that's where we begin to see how different our intuitive sense of time is from the way the universe might actually treat it. 'Cause when you dig into the physics of time, the ground doesn't hold as firmly as you'd expect. Take two clocks. They're identical. One stays with you on Earth. The other you send into orbit, or put on a fast-moving spaceship. When they come back together, they won't agree. The one that moved faster or spent time farther from Earth's gravity will have ticked at a slightly different rate. Not because it was broken, not because it malfunctioned, but because time itself flowed differently for it. This isn't science fiction. This is measured, proven. It's one of the core predictions of Einstein's theory of relativity, and it has been confirmed again and again. According to relativity, time is not absolute. It's not a background constant like a ruler laid out across the cosmos. It's flexible. It depends on speed and gravity. It's affected by motion and mass. And this flexibility isn't a minor detail, it's fundamental. It's the reason GPS systems have to adjust their internal clocks constantly. Satellites in orbit experience time at a slightly different rate than devices on the surface of the Earth. If we didn't account for that, your navigation would drift by kilometers each day. Even small differences in elevation can cause small differences in time. The top of a skyscraper ages slightly faster than the bottom. Your head is by the tiniest margin older than your feet. It's strange, but it's real and it's measurable. So when we ask whether the universe knows what time it is, we have to be careful, because even here on Earth there's no single answer. Time is not the same everywhere. It doesn't tick at the same rate in all locations. It doesn't even tick the same way for all people. Not in a physical sense, and certainly not in an emotional one. This brings us to a deeper idea. If time behaves differently depending on where you are and how you move, then maybe it's not time itself that matters, but space-time. The combined structure that links space and time together into one fabric. Einstein's insight was that space and time aren't separate. They are part of the same thing. And that thing bends, it stretches, it curves around massive objects like planets and stars. Those curves don't just affect space. They affect how time flows too. In a way, mass tells space-time how to bend. And that bending tells everything how to move, including clocks, including you, including light. When you stand on the surface of the Earth, you're not just feeling gravity as a pull. You're feeling the shape of space-time. You're resting in a curve. And in that curve, time moves at a slightly different pace than it would in deep space. That's not poetry. That's the geometry of the universe. But the geometry isn't fixed. It depends on what's nearby, on mass, on motion, on energy. So now we're starting to see how difficult the question really is. Does the universe know what time it is? Which time? Whose time? Where? And what would it even mean for the universe to know something? It helps to pull back for a moment and consider how we experience time in the first place. We don't feel the bending of space-time directly. We don't sense relativity. We live in what feels like a steady forward flow. One second after another, one event following the next. That's time as it appears to us, a straight line, a constant rhythm. But relativity tells us that line is only one possible path through a much more complicated landscape. A landscape where different observers can disagree on the order of events, where what's simultaneous for you might not be simultaneous for someone else, where there is no universal now. That might be the hardest part to accept. We like to believe in a shared present, one common timeline unfolding across all of space. But physics doesn't give us that. The laws of the universe allow different regions, different observers, to have their own slices of time, their own clocks, their own sequences. And in that kind of universe, the idea of a single time, a single answer to what time it is, starts to fade. It's not that time disappears. It's just that it becomes local, personal, a property of your motion, your place in the fabric, your journey through space-time. That raises another question. If time is so deeply tied to movement and gravity and location, then what happens in the parts of the universe that are empty, far from stars, far from motion? Is time still there, ticking quietly in the background? The answer depends on how you define there. One approach is to say yes. Time exists wherever space-time exists. The geometry is still present even if there's nothing in it. But if there's no change, no observer, no clock, no process to mark it, then time becomes invisible, not absent but unreachable. There are theories that suggest time might not even be fundamental at all, that it might emerge from deeper processes, quantum events, entanglement, entropy, that it might not be something the universe has, but something that arises when certain conditions are met. It's an idea still being debated, still in development. But it suggests something profound, that time might not be part of the foundation of reality, that it might be a feature of the way we interpret patterns, a shadow cast by change. And if that's true, then the universe wouldn't know what time it is because time wouldn't be something that exists for it in the first place. It's a hard thought to sit with. We're so used to time being constant, unavoidable, simple. But the more you look at it, the less simple it becomes. Even the idea that time flows forward, that the past becomes the present, and the present becomes the future, isn't guaranteed by the laws of physics. Many equations work the same in both directions. The universe doesn't seem to care whether something happens forward or backward in time, and yet we experience a clear direction, a one-way street. That's something we'll explore more soon. But for now, we're just letting the quiet questions settle. What is time really? And if we can't define it completely, or measure it universally, or agree on when now is, then what kind of thing is it? That doesn't mean time isn't real. It just means it might not be what we assumed. And maybe that's the point. You're lying still now in your own moment, your own place in the fabric, your own speed, your own gravity, your own thoughts shifting slowly forward. Someone else somewhere else might be doing the same, but their clock is ticking just a little differently. Not broken, just shaped by where they are. And that difference isn't a flaw, it's part of how time works, part of how the universe is built. So if we ask again, does the universe know what time it is? Maybe the answer is this. It doesn't need to, because there isn't one answer to give. But that's just the beginning. You've probably worn a watch or glanced at your phone to check the time, or seen the blinking digits of a microwave clock flashing to a las after a power outage. It seems obvious that all clocks, if they're working properly, should agree with one another. If they don't, something must be wrong. One of them must be slow or fast or broken. But that idea only holds in everyday life where speeds are low and gravity is steady. In reality, clocks don't always agree, even if they're perfect. And it's not because they're malfunctioning. It's because the universe doesn't treat time as uniform. Start small. Imagine you and someone else each have an atomic clock, the most precise type of clock we've built. You synchronize them. They tick in perfect rhythm. Then you give one clock to a passenger boarding an airplane, and you keep the other one with you on the ground. The plane takes off, flies a few hours, then lands. You meet back up and compare the clocks. They're not the same anymore. The one that flew on the plane has ticked slightly less time than the one that stayed on Earth. It's a small difference, a fraction of a second, but it's real, and it's been measured. Not just once, but over and over. You can even measure it with highly sensitive clocks on mountaintops versus those at sea level. The elevation alone, the change in gravity, is enough to create a measurable time difference. The principle is simple, even if the outcome is strange. Time moves differently depending on how fast you're going and how strong gravity is around you. This is Einstein's theory of relativity at work. Special relativity tells us that when an object moves quickly, especially close to the speed of light, time slows down for it relative to someone who's standing still. General relativity adds something else. Time also moves more slowly in stronger gravitational fields. Gravity curves space and it bends time with it. On the surface of Earth, we're in a gravitational field. If you are farther away from the planet, say on the International Space Station, you would experience time just a little faster than someone down below. Again, the difference is tiny, but it's not theoretical. It's real. We build our satellite systems around it. Your GPS would be completely wrong without those corrections. Without accounting for both motion and gravity, your phone could put you miles from where you actually are. The world we've built assumes time is consistent, but the systems keeping it running all account for the fact that it's not. Now, take that same idea and apply it to something far more massive than Earth, a black hole. Black holes don't pull you in like vacuums. They don't suck things toward them like people sometimes imagine. They're just regions where masses collapsed into such a small volume that the curvature of space becomes extreme. You could orbit one safely if you stayed far enough away, but as you get closer, time starts to behave differently. Let's say you could hover just above the event horizon, the boundary beyond which nothing returns. You're not falling in. You're holding position with powerful engines staying at a safe distance. From your perspective, everything seems fine. Your heart beats normally. Your thoughts flow. Your clock ticks forward like it always does. But if someone were watching you from a great distance, they'd see something very different. They'd see your movements slow down, your signals stretch, your clock tick more and more slowly. To them, it would look like you were frozen in time, hovering at the edge of the black hole forever. You wouldn't feel this change. That's important. From the inside, everything would feel the same. But from the outside, time would be stretching. Not just the perception of it, but the structure itself. This isn't speculation. It's predicted by Einstein's equations and supported by everything we know about general relativity. The closer you are to a massive object, the slower time passes for you compared to someone farther away. This leads to some strange possibilities. You could spend an hour near a black hole and come back to find that years had passed for someone who stayed farther out. The difference could be dramatic, centuries, millennia. It depends on how close you get and how long you stay. That's what time dilation really means. Not just a shift in experience, but a physical change in the passage of time. Your clock and someone else's don't just disagree. They represent different timelines. Both are valid. Both are real. But they unfold at different rates because the environment around them bends space-time in different ways. And if time can stretch this way, it raises deeper questions. What exactly is time stretching into? What allows that stretching to happen and how far can it go? In the framework of relativity, time is one axis of space-time. Just like up, down, left, and right are in space. Massive objects don't just bend the space around them, they also bend the direction of time. When you approach a black hole, it's not just that you feel pulled inward, it's that time itself is curving toward the center. Staying still requires enormous energy. Falling inward is the natural path, and as you fall, your time slows relative to the outside world. It's not something you could override. It's not a feature of your perception. It's built into the fabric of reality. The first time this became a topic of public imagination was probably through science fiction. Stories about astronauts returning home to find centuries passed, ships orbiting massive stars to stretch out time. But the idea comes from real physics, from the fact that gravity, not force in the classic sense, but curvature controls how time flows. In 1976, the gravity probe experiment launched a hydrogen MA clock aboard a suborbital rocket. It flew 10,000 kilometers into space and then fell back. During the flight, scientists compared its timekeeping to a reference clock on Earth. The spacepore clock ticked slightly faster, exactly as general relativity predicted. The difference was tiny, about 1 part in 10 million, but it was there, confirmed, repeated, built into our models of reality. Now take that idea to a larger scale. Near the center of our galaxy is a black hole millions of times more massive than our sun. It bends time around it in ways we can't directly experience, but we can observe the effects. We've watched stars orbiting close to that black hole. We've measured how their light shifts, how their paths curve. We've seen that the time those stars live through is not quite the same as the time we experience here. From that, we learn something important, that time is not a universal stage. It's a set of local conditions. It depends on the shape of space-time in each region of the universe. And that shape is not fixed. It changes with motion. It changes with gravity. It changes when mass moves, when energy shifts, when systems evolve. That means time is not just something we travel through. It's something that reacts, something that bends, something that changes shape. We see this in gravitational lensing. When light from distant galaxies is bent around massive objects on its way to us, that bending isn't just a curve in space. It's a shift in time. The light takes longer to reach us. It follows a stretched path. The time it carries is not the time it left with. It's shaped by what it passed through. And now we're starting to build a clearer picture. Time is not an absolute measurement. It's a local one. It depends on your path, your environment, your proximity to mass and energy. And because of that, a moment is not a fixed thing either. When you sit in a chair and breathe slowly, your moment is not the same as someone else's. If they're moving quickly or resting on a mountain or traveling through space, their moment is slightly different. The second is not your second. And when you both look back, your timelines won't match up perfectly. That difference won't matter much for most of your life. But it matters for understanding how the universe works, because it means that the idea of a single global now doesn't hold. The universe doesn't have one clock. It has billions, and they all tell time a little differently. So when time stretches, it's not breaking. Is behaving exactly as the structure of reality tells it to. That idea becomes even more important when we think about the early universe. Right after the Big Bang, when space was hotter, denser, and expanding quickly, the curvature of space-time was extreme. That means time flowed very differently then than it does now. The rate of time was tied to the expansion. The timeline of the cosmos isn't just long, it's uneven. The universe has lived through moments that pass more quickly or more slowly than ours. And there may be regions now far from us, cut off by the speed of light, where time flows at a different pace because of different structures, different densities, different gravitational conditions. In that context, the question, what time is it now, becomes impossible to answer for the universe as a whole. There is no now that covers everything. There are only local nows, nearby timelines, threads that move parallel but not in perfect step. And once we accept that, we begin to understand why time seems to stretch. It stretches because the universe is not flat, because gravity is not uniform, because motion is relative, because space-time curves. And that curvature is not just a shape, it's a tempo, it's a rhythm. It's the way each place measures its own passage. You're living in one of those places. Your timeline is yours. Your seconds are shaped by the planet beneath you, the speed you're moving, the energy around you. You don't feel it changing, but it's changing all the same. And out there, somewhere else, another clock is ticking a little differently. Not faster or slower in a broken way, just different. Because that's what time does. It stretches. Most of the universe is empty. Not in the way a room feels empty, but in the literal physical sense. Between stars, between planets, between galaxies, there are vast stretches of space where almost nothing exists. No air, no light, no sound, just distance, just vacuum. You might imagine that nothing happens in these places, that they're quiet, still, timeless. But even in the emptiest parts of the universe, time continues to pass, or at least that's what we assume. Out there, far beyond the edge of our solar system, where the sun's gravity begins to loosen its grip. There's no clock ticking in the dark. There's no signal marking the hours. And yet things still change. Particles drift, radiation spreads. Gravity pulls faintly on dust that hasn't yet found a home. It's hard to imagine time moving through that kind of silence. There's no rhythm to hold on to, no heartbeat, no light dimming or brightening. But the structure of space-time doesn't disappear just because things get quiet. The geometry remains. And according to everything we know, time continues slowly, steadily, invisibly. If you sent a spacecraft into that darkness, its onboard clock would keep ticking. Its systems would log every second. But those seconds would be different than the ones you experience here. The spacecraft, far from strong gravity, would feel time slightly faster. Just like we discussed before, the deeper into gravity you go, the slower time moves. And out in the interstellar void, gravity is weaker than almost anywhere else. That means the breath between stars, those long, cold gaps in the sky, aren't timeless. They're just slow. Slow in a way that's hard to notice, hard to measure, slow in a way that feels like stillness. But even in that stillness, time is still there. And that's important because it reminds us that time doesn't need active.